Hello, hello. Hello. Oh, great. Okay. Okay, great. Can the people at home hear me? Okay, yes. Good. Thank you. Okay, as I mentioned, this page is good. I have to sit down. Okay. So as I mentioned, unfortunately, we have to do this makeup, but hopefully you'll find this useful. Actually, this lecture won't cover too much material, but you need to read. Why is there this echo? You need to read section 2.3.2 and section 2.5. We will skip section 2.4 on non-homogeneous Poisson processes. All right. So last time we ended off by talking about splitting and combining of Poisson processes. So let me recap that. So if we have two Poisson processes N1T, that's where we ended off. I think I should do combining first and splitting. Okay, so after we do this, we will talk about several examples. So we have N1 of T. This is a rate lambda 1 Poisson process, and N2, which is a rate lambda 2 Poisson process. And the important thing is that, let me just say N1 is independent of N2, so I don't have to write so much. Right, so these two Poisson processes are independent, and so now I can create a new process at each point in time. I think the sum N2 of T. Oh, by the way, I think we are very far away, so I will remove this mask, otherwise it's falling out. I hope it's okay. Okay, so N1 of T is equal to N1, N of T is equal to N1 plus N2. All right, so we have this relationship, and they are independent. That is the important thing. Then the theorem states that N of T greater than 0 is a Poisson process of rate lambda 1 plus lambda 2. Okay, so that's the combining part. That's the combining part. All right, so we can also talk about splitting. All right, so here we start off with N of T. It's a Poisson process with rate lambda. And at every point in time, if there's an arrival, then it gets classified as type 1, reps type 2, with probability P and 1 minus P. And this process of classification into type 1 and type 2 is independent of the Poisson process. Reps 1 minus P. Okay, so then if we look at all the type 1 arrivals and we collate them into a counting process, we can call it N1 of T. Then and type 2 process is N2 of T. Then we can then we have the following theorem that N1 of T is a Poisson process with rate lambda of P, I guess. And of course, M2 of t is a Poisson process with rate as expected, with rate lambda 1 minus p. And furthermore, the entire process N1 is independent of N2. At least we proved the first two parts. Okay, we didn't prove the independence, but that's an exercise for you. So that's where we left off last time. All right, so I just want to do a small recap. Can see, right? Oh, Muhammad Yosef, I got echo. What can I do? Maybe I use the other mic. I don't know whether that's going to solve the problem. Okay, now is it marginally better? Hello? Okay. So the people here still can listen, right? Okay, good. Okay, so now let us do an example. And these sort of simple examples will certainly be examined, okay? So let S1K be the epoch of the kth arrival of Poisson process 1. Okay, and Poisson process 1 has rate lambda 1. Right, so as you can imagine, what I want to do is to create two Poisson processes and then label their arrival epochs. Okay, so as usual, as expected, we will have a new Poisson process that's x2j be the epoch of the jth arrival of Poisson process 2 with rate lambda 2. Okay, so we can call the Poisson process 1 N1 of t, that's a Poisson counting process, and this is N2 of t. Okay, so let us do a simple exercise question. And by the way, feel free to ask questions. And those people here, I cannot really look at the chat there. So if there's something very pressing, right, let me know. Something very important. Okay, I think all the people are admitted automatically today, which is good. Okay, so we want to understand what is the probability that S1K is less than S2J. So this is a simple calculation. Okay, so what is the meaning of this in English? That is the probability that the kth arrival epoch of first process occurs before the jth arrival of second Poisson process. So that's the meaning. Okay, so we want to figure this out. So when we do these sort of things, before we do anything, we should draw a picture. All right, so that's what I'm going to do. So this is time. We start from 0. And I'm going to label the first process as maybe blue circles. Okay, so let's say for the sake of simplicity and concreteness, that k is equal to 3 and j is equal to 4. Okay, so these are indicated by O, all right, by circles, and my j is equal to 3 and k is equal to 3 is indicated by crosses. Okay, so what is the meaning of this sentence here? All right, the kth arrival the kth arrival, so what is k here? K is 3. All right, so what is the meaning of S1K less than S2J? All right, so let's make this more concrete. This is the probability of S13 less than S24. So let's make this concrete. What must happen for this to happen? Think about it. Okay, so what we have here is, let us indicate these are the arrivals S11, S12, S13. It must occur, all right, if you look at this, S13, which is this guy here, must occur before the fourth arrival of the second process. Okay, and so that is indicated by what I'm going to draw next. Okay, so we could have S21 be here and S22 be here. Okay, and S23 maybe be here. But S23 must occur before this point here. You agree? Let me repeat. This is super important because I set exam questions of this. And this is also very important when you think about things carefully. Let me repeat. Okay. So what's happening here is I'm interested in this event. Okay, S24 here. S13 is less than S24 here. What must happen? What beautiful events must align for this to happen? Think about it carefully. All right. So I indicate my arrivals for the first process as red crosses. I indicate my arrivals for the second process as blue circles. Cool. Now, so I'm going to put down my red crosses in an arbitrary fashion. Here, here, here. So in order for this event to occur, the third red cross must come before the fourth circle, blue circle, which means that the third blue circle must be at most at this point here, because then the fourth circle will be somewhere here. All right, so my third circle is here. I could have pushed it up to here. All right, so my third circle is here. I want to get rid of the circle only. Okay, but it could be really close here. So this could be my S23. As long as it occurs before the S13, then my S24 will be somewhere here, over on this side. Right?
But if the third blue circle happens after the third red cross.
Oh yeah, that is also possible. Yeah, sorry. So your third circle could also be here, S23. Okay. So yes, so we have this situation, then your S24 could also be here. Right? So in fact, we could have this S22 be here also. I was mistaken, sorry. So if we think very carefully, what must happen for this event here to happen? All right. So now let us define things carefully. All right. How do we think about this? The way we think about this is we consider a combined or merged process. Okay. So this combined or merged process is any arrival, whether type 1 or type 2. It has rate lambda 1 plus lambda 2. Okay. So it's basically the combined process is basically regardless of whether we are blue cross or blue circle or red cross, we consider it as an arrival. And what is the rate? By the above theorem, the rate is lambda 1 plus lambda 2. Okay. So what do we need for this to happen? What do we need for this to happen? Let me just bring this out. Let's think about this carefully. Right. So, what we need for this event to happen, we need, let me just put down the statement, then we think about it. What do we need for S13 to be less than S24? Okay. So we need, out of the first, in this case here, let us look at this situation. Out of the first 7, out of the first 6, I'll explain this shortly. Arrivals of the combined process four or more switch to the first. So 4 or more of the first, 4 or more should be switched to the first process. And the first process is the one that is indicated by this. Okay. So let us see whether this is correct. switch to the, hang on. Okay. Let me look at this. So we have this situation here. Now, I may be marginally confused, but let me see. We want S24 to be bigger than S13. So this time, this is 0. Okay? So what happens here is that we have 3 arrivals here. This is S11, S12, and S13. It must occur, the S13 must occur before the 4th arrival of the second process. So it will here. Okay, so that's S24. Anything happens here, these 3 points can happen before, can happen anywhere. Okay, so out of the first 6, we need, is it 4 more? Okay. This should be 3 or more. Switch to the first process. So here we have exactly 3 that are switched to the first process. Okay, here the first process is the one in red. 3 or more are switched to the first process, and here we have the S24 coming along. Okay, so now let me write down something. Okay, we define P. Let us define P to be the probability of switching to the first process. The first one is the red one. Okay, so let us calculate what is the probability that exactly K are switched to the first process. Okay, so we have a total of K plus J minus 1. Right, here we have a total, I'm using this part here, K plus J minus 1. We have 7. We need to have 6 of them in total to talk about the total number, and we need K of them to be switched to the first process. So that's P to the power K, 1 minus P to the power K plus J minus 1 minus K. All right, which can be simplified to be J minus 1. Okay. Now, we can easily generalize this to the case in which we consider, so let me copy this. We consider exactly, say, I bigger than K are switched to the first process. All right, so now we can just get rid of this and call this I, and we have K plus J minus 1 minus I here. All right, so this is just nothing but a binomial distribution. All right, where this is the total number of trials, and this is the number of successes. Okay, and the success probability is P. Okay, so in this example, the first process is the one that is in red. In order for S24, sorry, wrong pen. In order for S24 to be bigger than S13, all right, we need out of the first 6 here, we need 3 of them to be switched to the first process. Could we have 4 switched to the first process? Suppose we have this, right? 4 switched to the first process. Then that's also fine. Okay? Because if 4 switch to the first process, we can call this S14. Then S24 is certainly, if S24 is bigger than S14, by definition, S14 is bigger than S13. So we are also okay. All right? So we need out of the first, to generalize this number here, K plus J minus 1, total number of arrivals minus 1. All right. This one here is K, or more, switch to the first. So let me repeat, look at this picture, all right? Suppose, so this is our 3 plus 4 minus 1. And this is 3. Now, let's look at this situation. This is 6. Okay? I always like to use numbers. So out of the first 6 arrivals here, let's say 3 are switched to the first process. Okay? These 3 are switched to the first process. Then certainly, this one will be after my S13. Okay? Now, 3 or more. So what could I have many here? Yeah, because now this will be S16. All right, S24, if S24 is bigger than S16, then and certainly S16 is bigger than S13, this is also fine. This is more relaxed. Okay, so now I calculate exactly K are switched to the first process. Out of this total, okay, this is just for preparation, exactly K. So what am I doing in this particular picture that I've drawn here? This would be 6 choose 3, p to the power 3, 1 minus p to the power 3. Okay, this is this calculation. But I cannot forget about the possibility that many more are switched to the first process, right? So I do a more general calculation here, more general calculation. All right. So in general,
the last equation, the PK should it be PI?
PI, thank you, typo. Thank you. All right. So in general, in conclusion, the probability that S1K is less than S2J. What is the meaning of this? That's the probability that more than or equal to K, let me just say at least K, all right, are switched to the first process. First process out of how many? Out of K plus J minus 1 combined arrivals. Combined arrivals. And I already explained this using the picture. I will explain one more time. This is super important. So this is nothing but, okay, I will sum up. I will look at this equation of mine. What equation? This one. Okay, exactly I greater than K. So what's happening here is this. And I will sum up from I running from K to K plus J minus 1. Probability of exactly I, we don't need this, are switched to the first process. Right? So that is basically splitting up what this expression means. Okay, greater than or equal to K. So I'm just running through all possible K, all possible I's that are at least K up to K plus J minus 1. And now basically we can just substitute in the formula for this. So I could have just copied this. Okay, here. Right? So this is a little bit tricky, but this actually shows you the power of combining and splitting. Okay, so let me go through this one more time. Okay, let me just get rid of this intermediate calculation. All right, so it's best to think about a specific example where K is equal to 4, K is equal to 3, J is equal to 4. That's my example. And I'm interested in this probability. All right, and actually to do this is very difficult. All right, because even though these two are independent, all right, if you want to figure out this event here, it's extremely complicated because this is an Erlang distribution, this is an Erlang distribution. So what do you do here? So you have to do some very complicated conditioning if you do not know the theory of Poisson processes. So you have to condition on this being a certain value and then integrate over. That is what you will do if you don't take this class. But if you take this class, you will do something smarter. And when you do something smarter, you have to think what is the physical interpretation of this. So you have to draw a number line and you put some values in. Okay, you always have to put some values in. Say K is equal to 3 and J is equal to 4. Then you have this situation here. This is a successful situation where out of the first k plus j minus 1, the first 6, you have 3 successes. 3 successes. Okay? Success means it's crossed. All right? Then what does that guarantee you? That guarantees you that no matter what happens over this side here, right? No matter what happens over this side, beyond, no matter what happens here, you are going to succeed. All right? What can happen here? Red can come or blue can come. All right? If red comes, we have a red point here. All right? But nevertheless, with probability 1, some blue point will come. But whatever happens, the blue point will be after this red point here. Okay? So we have to be careful. All right? Out of this first 6, we need at least 3. And this is what we are calculating here. Okay? So this is the important calculation. This was just a preparation. Okay, this is the important calculation. Exactly I greater than k are switched to the first process in the first k plus j minus 1 arrivals. Right, just to be pedantic. And we have this. This is a binomial distribution. And then we just plug in. Any questions? This to illustrate splitting combining. Any questions from the audience here? And any questions from the Zoom people? Let me pause for a moment to see whether the Zoom is okay. Is this absolutely clear from the people here and the Zoom people? Okay. We are in no rush. Is this clear? Any questions? I think I went through this slowly and walked through it slowly. Okay, so if there are no questions, let me move on to the next example, which is also interesting. Okay, so this class actually prepares you very well for subsequent classes if you take here at NUS or elsewhere on queuing. So I am not, how to spell queuing? There's so many. Queuing, let's just do it the standard way, queuing. So let us consider what is called an MM1 queue. And this sort of thing is studied very regularly in the, let me not put this embarrassing thing, I don't know how to spell queuing. All right, this sort of thing is studied very regularly in operations research, where we want to serve customers, right? What's the best way we can serve customers, whether our shop is big enough in order to serve the customers that walk into our shop, because our people who serve the customers will be very slow. So we want to understand things like equilibrium and stability. All right, so an MM1 queue. So in queuing, we have this sort of convention where we have these 3 letters here, right? You often see MG1 or MGKQ, all right? But this is the simplest form of queue. What does M stand for? So the first character here, M, which is M in our case, stands for memoryless process, memoryless arrival process. So the people in your shop arrive according to a Poisson process. All right, if the inter-arrival distribution is exponential, memoryless arrival process, exponential. Inter-arrival times, which means Poisson process. So here we are basically saying the same thing. Okay, so the second character here, M, denotes memoryless service time. So basically, when a customer walks into your shop, you serve him or her, right? When the customer walks into a bank, goes to a certain teller, and then the teller serves him or her according to a memoryless process, the service process. So this is the arrival process, is the service process, slightly different. The third character here, here in our example, our third character is 1, right? and this denotes the number of servers. So at a particular point in time, when I walked into the bank, there was only one available teller. The rest were all sleeping. Okay. So of course, this is a very, very simple process. The arrival and the service times, they are all memoryless. So we have a lot of theory of Poisson processes. And here we only have one server, so there's nothing much to worry about. Whether the server is still serving someone, how many people are ahead of you in the queue, and then how long you have to wait for that particular server to be available to serve you. Okay, so here we are going to consider, and this will lead. This is the way to spell queuing. Queuing system with arrival of customers following Poisson process lambda. Okay, and we consider here a single server queue that serves customers with a service time distribution that is exponential mu. Of course, this is also going to be something like a Poisson process. It's not quite a Poisson process, but the service times are exponential distributed, because here you could be serving no one. All right. So if there is a customer that comes to the teller at the bank, then he or she is served, and the service time is exponential mu. All right, mu and lambda don't have to be the same. So before we do anything, let us do a thought process. All right, it could be that lambda is bigger than mu, lambda is equal to mu, or lambda is smaller than mu. These are the three scenarios, right? So what are we going to prove in this simple model? So if you have a lot of customers arriving relative to the number of servers in the bank, what do you expect in the long term? Then a lot of people will be queuing, right? And so a lot of people will be queuing up, and you will not be able to serve everyone. Now, in this other case here, you are very efficient because you have one teller, and it's the other way around. So basically here, your service time is longer than your arrival time. So here you will have the situation that you will have a very long queue eventually. This is a very long queue. You will have a lot of customers bunching up. And here you will have no problem serving the customers. So let's try to look at this mathematically. So there are only three situations here. And we will look at these three situations shortly. Okay, so you can also think of this in terms of a buffer and packets. Okay, so here is a buffer. You can think of this as a buffer queue. So people are queuing up for their favorite burger, for example. And then here is the server who serves the burger. Okay, and lambda packets or lambda people per second enter lambda packets per second enter the queue. And then they are served, and the server serves mu packets per second. So that's the situation. Lambda packets and mu packets. So basically you enter, packets enter the buffer. So this is basically trying to illustrate that you have one packet here and another packet here, and so on and so forth. All right, here you have four packets that are lined up. And then the server is going to serve the first one. First in, first out queue. All right. So we want to sort of model this situation. And we want to prove something that corresponds to our intuition that if you serve faster than people come, then eventually you will have no people in the queue in the long term. Right? As we take limits. Okay. So let us consider, for example, the situation. Let us draw something as follows. Okay, so let us consider the following. Okay, so how many? Let's consider. Let state K denote that there are K customers in the buffer or queue. Right? So we can have we basically have k customers in the queue. So in this particular situation, the way I've drawn it, we have 4 customers in the queue. They have yet to be served. Finished. They have yet to be finished served. Okay. So basically, we can model this according to the following state diagram. So how many people can there be in the queue altogether? You get infinitely many people. All right. So you basically what I'm going to do is the following: 1, 2, 3, up to k. Continue on. Okay. So if you have no people in the queue, at all at this point in time, all right, what is the chance that you will have 1 person in the queue? What's the probability that you have 1 person in the queue? So 1 person counts. Lambda delta. Let's say that we are working with a small time interval delta. And as you know, for Poisson processes, the probability that 1 person arrives is lambda delta. Okay? And we are always talking about small time intervals of delta. So what is the probability that there are still 0 people in the next time interval? So I'm only considering time intervals like this. Only length delta. Okay? So in this simple scenario, okay, so what? Now I have 0 people in my queue. What's the chance that I will still have 0 people in my queue? It's 1 minus lambda delta. Right? So next thing here is, if I have 1 person in my queue, what is the chance that I have 2 people in my queue later on? Is basically lambda delta. But what's the chance that I have 0 people in my queue? Well, this guy will be served, right? Served. And so you will transition to 0 with probability mu delta. What's the chance that there will be exactly 1 person in my queue? If I'm at 1. So I'm here at this point. What's the chance that I will remain as 1 person in the queue? What things must happen for this to happen? 1 person in my queue. That means there must be no arrival and I must not be served. Finish. All right. But this you don't really have to calculate because all the outgoing arrows should solve to 1. You must go somewhere the next time. So we have that this is 1 minus lambda delta minus mu delta. So 1 minus lambda delta minus mu delta. And all these are the same. Okay? But we always increase by symmetry purposes. We always increase with probability lambda delta and decrease with probability mu delta. Mu delta. And we have countably infinitely many states. Okay? Lambda delta. So this is an instance of a Markov chain, which we'll study next time. So one more time, let me repeat. We are going to let state k denote that there are exactly k customers in my buffer queue. So in this scenario here, I have 4 customers. In this colorful scenario here, I have 4 customers in my queue. All right. What is the chance that I have 5 customers? All right. Lambda delta. What's the chance that what's the chance that this decreases to 3? That the person currently being served must be finished serving. All right. And the service time follows an exponential mu distribution. So this decrements with probability lambda delta. Okay. And so we remain with the remaining probability. So Pij, let us denote Pij as the probability of transitioning from state I to j. And here I and j can take on the following. Okay, natural number union 0. So all non-negative integers. The probability of me transitioning from state I to state j. So we always consider, as I already mentioned, delta infinitesimally small time interval. Okay, so we have this state transition diagram. By the way, this is called state transition diagram. Okay, so let us write down the state transition probabilities. So P00 is 1 minus lambda delta, and this is reflected here, right? P00 is reflected here. Now, P0, P of, in general, J plus 1. So this is my current, and this is future. That's the convention. Okay, it's lambda delta. This is the convention. You could switch it around also, but this is how people write it. P of J minus 1. Again, this is current, and this is the future. It's mu delta. And of course, you need to go somewhere. So you remain with 1 minus lambda plus mu delta probability. So basically, this is actually a countably infinite matrix, right? But I populated all the entries for you, right? So in this case here, okay. So this is just a remark here. This is a birth-death process. And we'll study this in much more detail when we talk about Markov chains after the term break. Okay, by the way, you have no term break because I'm having this class. So this is a birth-death process, because you can think of this as, oh, currently I have a certain population of people here, and then every time we give birth, then we have one more person in our population, and every time we die, we have one less person. So we want to mathematically study whether the population gets wiped out or whether we have overpopulation. Okay, so this is our current population, and say women give birth with probability this, and people die with probability this. We can still study this mathematically. Actually, these sort of things have been studied mathematically a lot. Okay, these are a lot of research. Okay, so when we study Markov chains, we will prove the following. At equilibrium, all right, in some sense, and you don't have to know this at this point in time, lambda pk equals to mu pk plus 1. Here k is in n. All right, at equilibrium, whatever equilibrium means. When we talk about Markov chains, we will also mention the word steady state probabilities. So the steady state probabilities pk are the long-term averages. Suppose I let this thing run. Suppose I let this Markov chain run for a very long time. Then what is the probability that we are in state k? That is what I denote here, the steady state probability. This is a probability in state k if I let the chain run. If the chain or the Markov chain is run for a long time. So we will prove this. We will prove this out of the equation here. This is called steady state equation. All right. So what we can do is the following. So we have that pk is mu over lambda. I think pk is mu over lambda over mu power k p0. Okay, this can be proved by induction. I will not do this. All right, so here we can let k be greater than or equal to 0. This can be proved by induction by plugging this into this, obviously. All right, things will cancel. Right, so this is a matter of solving this equation. But at the end of time, you must be somewhere. Right, so we have that we have the normalization condition that you must be somewhere. So the probability, the sum of all the probabilities, k running from 0 to infinity must be equal to 1. Right? So if we plug this in, we have lambda over mu raised to the power k of p0. So now p0 is a free parameter. We do not know what it is. It's equal to 1. All right? So it means that, and I'm going to use rho to denote lambda over mu p0. Okay, so it means that now I have k greater than or equal to 0. Rho k p0 equals to 1, and by something known as the geometric series formula, right? This is 1 over 1 minus rho. Rho is this quantity here, so that I don't have to write so much. What's wrong here? If you do this in some exam, after I teach Markov chains, you will get half the marks. Something is not very good here. No, my equation is okay.
P0 times 1 over 1 minus rho equals to 1.
P0 times 1 over 1 minus rho. Oh, yeah, my equation is wrong. Thank you. But modulo then, that is a big mistake. So this implies that P0 is equal to 1 minus rho. But this is still not correct. Something is not right. After taking my class, you will be very sensitive to this sort of thing because I don't like this. What was wrong here?
Rho cannot be greater than.
Thank you. Rho cannot be greater than. Yeah. So here we are implicitly assuming rho is smaller than 1. Otherwise, the series does not converge. And we are unhappy. Right? So this what we have done here and what you have corrected me is that we have made this assumption that rho is less than 1, then we have this formula here. And we'll see what rho less than 1 means. Okay. So let us make this assumption that rho is less than 1. Then what happens here is that we can write a general formula for pk, which is the initial probability P0 multiplied by rho power k. So this is nothing but this formula here written slightly differently after we have solved for the initial condition. Okay. So in this case, what is our average Q size? Okay, so that's nothing but the expected value of x, okay, which is nothing but sum over all possible values of k, pk, k bigger than or equal to 0. So we can do the following simple calculation: 1 minus rho k, rho power k, and this is you can evaluate this using different ways, like differentiating the series, rho over 1 minus rho, which is lambda over mu minus lambda. So we can compute things like this. Okay. So if rho is less than 1, what does this mean? What does this assumption mean? Rho is less than 1. This means that what is the meaning of rho in the first place? It's lambda over mu from this orange equation here. Lambda is less than mu. This means that the arrival rate is smaller than the service rate. Right? So intuitively, at this point, all packets will be served. All packets will be served before they accumulate. Okay, so if this is true, the arrival rate is smaller than the service rate, and all packets will be served, so you won't have a situation that you accumulate you accumulate too many packets here. Too many packets here. So you will serve, you will have a situation that you'll be served, and the distribution will be as follows. Okay, the eventual equilibrium distribution pk will be such that you have 1 minus rho at 0, so that is 1 minus rho, and then it will be geometrically decaying. This is 1 minus rho power rho, and so on and so forth. 2, so it will concentrate at 0, minus rho squared, 3, etc. So that is the equilibrium distribution. Okay, but there are several concepts here that I have not talked about yet, so you don't really have to worry too much about this. Okay. For example, Markov chains, this is just an introduction to Markov chains. We haven't really talked too much about this. So don't worry so much if you, for example, you do not understand where this steady state equation comes from. We will talk in great detail about this until you are fed up next time. Okay, but here we have actually shown that if the arrival rate is smaller than the service rate, then all the packets will be served before they accumulate at the buffer. And so we can finish serving everybody happily. Okay. So so any questions? Actually, there's not so much we can talk about here because this we have not really discussed too much about queues and about Markov chains, but we'll talk a lot about Markov chains in future. Okay. Any questions? Yeah, thank you. Sorry, I didn't. What is crystal? Because some people will be talking. Some people are talking here among themselves. Yeah, we need to make sure Jingyang. We need to make sure that we need to make sure rho is less than 1. No need in magnitude because rho is positive because all these are rates. Lambda over mu, the lambda over mu is positive. Okay. Right.
So that means lambda cannot be equal to mu.
Yeah, lambda equals to mu. This does not sum up also. Right. Lambda equals to mu. You would have the situation that lambda is equal to mu, of course, in practice, but this theory here and this calculation of the steady state probabilities, this does not work for this situation where we have countably infinitely many states. But it works when we have finitely many states. If we look at that situation when we talk about Markov chains, where we will only focus on chapter 5 of Markov chains where we have finite states. And that will simplify a lot of discussion. Okay. This does not work if lambda equals to mu as well. It does not work. By does not work, I mean this theory that I've just presented does not go through. But there are other theories that will go through. Okay. Right. So now I want to do yet another example for you that talks about splitting and combining. Okay. So let us consider a Poisson process with rate lambda. I'll write this like the following. Now we know if we fix t bigger than 0. We know that hopefully by now we know the distribution of nt. It is distributed as Poisson lambda t. This is what we proved last time. Yeah, we're working with a not differential equation. We're working with difference equation. Go and search it. So we're not dealing with derivatives, we're dealing with differences. Differences, and you can talk about discrete time dynamical systems or something like that. Okay. We are working in discrete time. You can also search it. Not finite time. Finite time is very funny. Okay, thank you. Well, in no rush. Okay. So where was I? I was here. All right. So we have a Poisson process at rate lambda, and we fix t deterministic time. Deterministic time. And we have a theorem that says the following. Last time we proved this. We proved this using several methods, including my method. Right? Poisson distribution. So what is my question now? Let t be defined as exponential random variable with rate mu. Okay. So this is independent of Poisson process lambda. We define a new random variable with Poisson with exponential distribution of rate nu. So let's remind ourselves what this looks like. FTT is nu e to the minus nu t, indicator t bigger than or equal to 0. Okay, so that's the meaning. So now we have two objects. One is our favorite, our friendly Poisson process, And another one is an independent random variable, which is nothing but an exponential with rate nu. So question. So we would like, what is the distribution of NT? Aha, big difference. This is T and this is capital T. So later on, I will show you. You see what's the difference? You look confused. Are you confused? No, okay, very clear, right? What is little t and what is capital T? Right? So now I'm putting in a random time. So here, what's the distribution of NT? What's the meaning of NT in English? It is the number of arrivals in the interval of random length 0t. That's the meaning. Is the number of arrivals in this random interval. The interval length is random. Open bracket on the left is okay. Yeah. That's the. Thank you very much for being so precise. I like it because this is the number of arrivals in this half open, half closed interval. Okay, so if you want to be very precise, it's okay. So let us try to figure this out. This is a bit non-trivial. So if you don't know about splitting and combining, which is the technique we will be using in 1 minute, what would you do? What is my favorite
Conditional.
Question in probability? Law of total something. Right? Law of total expectation. Whichever year I teach this class in, my quiz 1 will have this question. All right. So what we will do is law of total expectation. So what will we do? We will consider the particular random variable or probability. We will consider the NT. We will consider this particular random variable being equal to n. So that's the probability, right? And then we will condition on. On T, and then we will take out the expectation. Why? Why so complicated? Actually, it's not complicated. It simplifies the life. What is the insight here? It is nothing but probability NT equals to n, condition T is equal to T for a fixed little t. Then, I know that this is NT equals to n, condition T equals to T. Now, what do we use? Start with I. Independence. And we drop this. Now we are very familiar because I proved this last time. Flow of the inside, and then I'll take outer averaging. Finish. This is what you do if you are not aware of splitting and combining. But now let me show you a splitting and combining way to do things. Okay, so everyone understands this slow motion way. This slow way of doing things. You basically use law of total expectation. Okay, but that's not the purpose of my discussion here. Later, I'll show you exactly this calculation when I do the example. But now let me show you the fast method. Okay, so we want to get a handle on NT. So what we will do is view T as the first arrival of an a second but independent Poisson process of rate nu. Why? Because the inter-arrival times of a Poisson process are exponential. So T is nothing but the first arrival of a new and independent Poisson process with this particular rate nu. Correct? You agree? People at home agree? Yeah, my favorite thing is conditional expectation. Sorry, I cannot turn backwards. All right. So we can view this and we can merge the new process, a new and independent process. Let's call it the new process with the old one, with the rate lambda Poisson process. With the rate lambda Poisson process. Okay. So in particular, each arrival of the merged Poisson process is the original one with probability 1. It's the lambda over lambda plus nu. Correct? And it is the new process with probability nu over lambda plus nu. All right, so this goes with this, and the original one goes with this. This is the original with this probability, and the new one is probability. Okay, so the idea is as follows. Okay, so we have this times 0, and we have the rate new one. The new one is in red. This particular arrival here. Okay, so this is the rate new process, Poisson process. Okay, and what is the meaning of NT? What is the meaning of NT? So this is the arrivals of the rate lambda Poisson process. What is the meaning of NT? NT is the number of arrivals of the purple process here. You agree? It's the number of arrivals of the purple process in this part of the interval up to this point here. You agree? Yes. Okay, so we want to have this picture in our head. Otherwise, we cannot do things. All right. So let us define a few key quantities. Let K be equal to the number of arrivals until the first success, where success is defined as the arrival. Success is defined as the arrival of new process. So in this picture, okay, how many arrivals until the first success? 3, because I drew 3 circles. Okay, so what is the distribution of K? Well, this happens here with this probability. And this happens here with this sort of probability. Right? This is the new process. The red one is the new process, and these are the original process. Okay, and we have these probabilities. So what's PKK? It's nothing but new. Okay, let me use the black pen. New over lambda plus nu, lambda over lambda plus nu, K minus 1, where K runs from 1 to all the way. Number of arrivals until the first success. Okay? But what we really want is NT. Okay? You can see that NT is equal to K minus 1. You could have 0. Okay? You could have 0 arrivals of the original process. Actually, I didn't have to do K. I could have just done NT, which is K minus 1. And so P and T, okay, you could have 0, you could immediately have this success here and nothing before it. Right? So NT can start from 0. So this is already, you think that this NT, you're not correct because it starts from 1 here. This geometric distribution starts from 1. Okay? So NT is K minus 1, and in particular, we need to shift this a little to be the following. NTN is equal to nu over lambda plus nu, lambda over lambda plus nu to the power of n starting from 0. Okay, Okay, so what do we have to do when we come out with a distribution so that we don't lose all our marks? Like 50% of people here, when I ask for a distribution, you give me something. Okay, you don't give me something negative, which is good, but you give me something that does not add up to 1, you immediately get 0. All right, so this, let me call this P, let me call this 1 minus P. Hopefully this adds up to 1. Yeah, it does. After we apply the geometric formula in our head. Right, so if we compensate this by this sort of thing, or plus or something, then you will not get 1, and so it's very bad. All right, so this is, so you notice what we have done here. All right, we have thought of the random variable nt as the number of arrivals of the purple process before the red arrival, the first red arrival here. Okay, and this is a geometric distribution that starts at 0, because you could immediately have an arrival of the new process. Nothing is precluding that. So there must be some positive probability at n equals to 0. So immediately you know it is this. Okay, immediately you know that n has to start with 0, and this is a geometric distribution. Geometric distribution is a very tricky thing because you can start from 0 or 1. All right, but in this case here, nt can take on the value 0. And so we have this distribution. It must start from 0. And we always have to do a sanity check. Put p, p1 minus p here, and make sure it sums up to 1. And in this case, it really sums up to 1. Any questions on this? This is number of arrivals. When I say arrivals, I mean inclusive of old and new processes. Okay, this is the meaning, not just the old one. Okay, now here I define number of arrivals of the lambda process, the old process. Okay, so again, I'm going to pause to let people ask questions here. Any questions on this? Any questions on this example here? This is super important. You will get to play with this. I specially designed a question in the next homework on this. So my homework question is, oh, okay, very simple. Now let's consider a Poisson process with rate lambda. Let's consider another random variable independent of the original Poisson process, Erlang of order L. So you will have L arrivals here. And so what is the total number of purple points before the L arrival of the independent Poisson process of order new, of rate new? Okay, that's my homework problem. Okay, you understand? So suppose we consider Erlang process, Erlang random variable of order 2. Then we have this situation. How many purple circles, all right, come before the second arrival of the new process? Okay, so that situation, that random variable is called a negative binomial. It is a generalization of the geometric. Okay, so we can make up several interesting situations like this. Okay. All right, any questions on this? Any questions? Is this very clear? Someone will tell me crystal again. Okay, so now let me prove one more theorem and then we will take a small break. Okay, right. So this is what follows. I'll be discussing section 2.5 on conditional arrival densities. Okay, which is the last thing we want to talk about in Poisson processes. Conditional arrival densities. Okay, so now what is the question? Condition on event nt equals to n Okay, clearly there are n arrivals in 0 to t, exclusive, inclusive. Right? We know this. We know that there are n arrivals here. So what is the distribution of S1, S2 up to Sn? So what is the story here? Remember how I motivated Poisson processes by football games 3 weeks ago? 3 weeks ago. So you walk into the living room and the football match is ongoing, and you see at that point in time that you watch the football match that 10 goals have been scored. It was 5-5. So what is the distribution? And you came in at the 70th minute. What is the distribution of the arrival of the 10 goals? All right, so we have this situation. All right, you came in at nt equals to n, and there were 10 arrivals here. So how are they distributed in this interval here? There were 10 goals here. So where is the first goal on average? We will prove theorem. There is T over 11 here. There were 10 goals. Okay, in general, okay? T over n plus 1. There were n arrivals. This point here is Sn, this point here is S1. All right. The expected location of S1 is T over n plus 1. That's the theorem that we're going to prove. So when we at a particular deterministic time t, we came into the living room and then we saw that 10 goals were being scored on the TV. The distribution of the first goal, where it is located, the expectation of the first goal is a random variable conditioned on this particular event. Okay, and it is at t divided by 11, n plus 1. This is the theorem. Is the theorem clear? You know what we are conditioning on? Okay, of course I need to write a more formal statement, which will prove. So the punchline is that, okay, suppose we are in a simple situation that nt is just equal to 1. Nt is equal to 1. So S1 lives somewhere here. Nt is equal to 1. Then S1 is, in fact, what we're going to prove is that S1 is uniformly distributed on 0t. Now, some people will be objecting to this open close here. Okay, so S1 will be uniformly distributed here. And so its mean will be halfway between that t over 2. This is what we're going to prove in the next few minutes. Okay, but let me write down the formal statement. So here is n equals to 1. Here is n general. Actually, n, yeah. Okay, so that's everyone understands the story? Story, okay? Now, so theorem. Let f of Sn given nt. Oh, by the way, this S does not mean S power n, okay? Sorry. In the book, in Gallager's book, he does this. Okay, to denote the random vector as well as Sn. But I'm going to simplify this to this, okay? So that I don't have to put so many brackets. Okay, be the joint density of Sn equals to S1 to Sn given the event nt is equal to n. So this whole topic here is called conditional arrivals. What are we conditioning on? We are conditioning on having n arrivals, and we are interested in what is the distribution of the n arrivals from the interval 0 to t. In the interval 0 to t. So this is exactly what it's talking about. Okay. So the theorem is that this density is constant in the region given by 0 less than S1 less than S2 less than dot less than T. Okay, and so in particular, let's write this down carefully. Okay, and this is equal to n factorial over t to the power n whenever this thing here satisfies 0 less than s1 less than s2 less than sn less than t. Okay, so this s power n is shorthand for the vector s1 to xn. So you see here, what do you see? This guy here does not involve Sn. All right, so it must be constant in this region. Now, if you are outside this region, this density is 0. Okay, so this looks a little bit cumbersome and heavy. So let's consider just the following: f of s1, s1 is the same as s1, right? Okay. Let's consider f of s1, condition on nt of s1, condition on 1. So the number of arrivals is 1 up to time t. So we are in this second situation here, where we only see one goal when we walk into the living room. Okay, so let's specialize this. So it's 1 factorial over t, right? 1 factorial over t, 0 less than s1 less than t. Okay, let's just get rid of the 1 factorial. First and foremost, what do we need to check? What do we need to check? That this adds up to 1. Every time we write down a density, this should add up to 1. All right, so what do I do? I will integrate this dt. Correct? Integrate this, ds1 from 0 to t. I will do this integral in my head. And this indeed add up to 1. Okay, everyone see, we integrate this from ds1 0 to t, and this indeed adds up to 1. Can you see this? Do you want me to do this carefully? Okay, by the way, this is a uniform distribution up to t. This is 1 over t. This is f of s1 condition nt of s1 condition on 1. Okay, this is s1 axis. So this is the PDF. And the height here is 1 over t. The height here is definitely 1 over t, right? So here, so basically now we are constant when S1 is smaller than t. So this second result here is a specialization of the first result. You agree, right? Simple. Okay, so now we are going to prove this theorem here carefully. Any questions about the statement of the theorem before I do any heavy lifting? Actually, it's not very heavy lifting. After this heavy lifting or pseudo heavy lifting, we will take a toilet break. Any questions? Yeah, He Yifan, I forgot, I didn't see your question just now. So it's the number of arrivals. Hopefully I already answered your question. I think I answered the question. K is the random variable that is inclusive. NT only, if you interpret NT, it is the arrivals number of arrivals of the PP lambda type. Okay, so basically the O process. Okay, so hopefully this is clear. Ifan, clear?
Yes, Prof. I understand this because you define this at the end of the question, but
yeah, okay.
At the beginning, you also define NT as the number of arrivals in.
It should be NT is the number of arrivals of the O type, this OPP lambda type. Okay.
Okay, thank you.
All right. Yeah, unfortunately, I don't index, so you have to read my index. Okay, so let us prove this. Okay. Everyone, by the way, everyone understands the theorem statement. You must understand the theorem statement, otherwise the proof is filled out. All right. Okay, so this is not very difficult. Proof. Okay, let us start with the joint density of Sn plus 1, which is the vector. All right. So f of S1 up to Sn plus 1 of S1 up to Sn plus 1, what is it? Remember, and I'm not going to prove this again, it is just dependent on the last time. Lambda n plus 1 e to the minus lambda Sn plus 1 when 0 less than S1 less than, and I'm not going to be careful about the less than equal, okay? Sn less than Sn plus 1. Okay, so now we want to derive, our goal is to derive this object here. Okay, so by base rule, we have f of Sn plus 1 given nt equals to Sn plus 1 given n, p of nt equal n. Okay, so it's by base rule, p of nt given Sn plus 1, n given Sn plus 1, f of Sn plus 1, Sn plus 1. Hopefully everyone is very familiar with base rule. Okay? So we're going to figure out all these four terms. We're going to figure out all these four terms carefully. All right? So the first thing we are going to figure out actually is we already, okay, we need to, we have, it's easy to do this. This is nothing but Poisson random variable, Poisson distribution. All right, so we need to figure out the rest of the three. Okay, so the first thing that we are trying to tackle is this term here. All right, this term is easy, it's 1, 0. It only takes on two values. Okay, so note that nt equals to n if and only if t is less than or equal to Sn and Sn plus 1 is bigger than t. So this is the picture you want to have in your head. So this is t, this is Sn, and Sn plus 1. Okay, then in this case here, nt is equal to n. All right, now you could have the situation that this line here is exactly here, but I don't want to draw this sort of situation. Okay, you just have to be aware that you can have equality here. But so nt equals to n means the following. Okay, so what is the distribution p of nt given Sn plus 1, n given Sn plus 1? This is equal to 1 if Sn is less than or equal to t and Sn plus 1 is bigger than t. And 0 otherwise. Okay. So this is exactly the situation here, right? So if Sn plus 1 is bigger than t, and this is conditioning on the entire set of arrival epochs. The entire set of arrival epochs takes on this value Sn plus 1, which is this, let me just remind you, is this factor S1 up to Sn plus 1. So there's a particular realization. We have this particular realization here. This guy here is equal to 1 if n here, if the number of arrivals here is exactly n, which means this situation here. Sn is less than or equal to t, and Sn plus 1 is greater than t. This entire, you need to have this vector here, have the last two elements satisfy this condition. So the last two elements are Sn plus 1. Clear? So we are tackling all these terms, term by term. We have already tackled this guy here. This guy is this deterministic distribution. Is equal to 1 if this is true, and 0 else. Any questions here? This is a little bit tricky. But you need to know the picture. The picture will guide you. So now, this is a particular realization of the arrival epochs. We are fixed to this sequence here. All right? When is this feasible? When is this logical? When is this possible? It is possible if at time t, we have n arrivals. But at time t, we have n arrivals means that Sn must be less than or equal to t, and Sn plus 1 must be bigger than t. Okay? So this is equal to 1 only under this situation. Otherwise, it's not possible. 0. Okay? So now we just restrict our attention to the case nt equals to n, and Sn is less than t, Sn plus 1 is bigger than t. Then we have f of Sn plus 1 given nt, Sn plus 1 given n is equal to f of, okay, so now this guy here takes on the value 1. I'm restricting my n and my Sn plus 1 to satisfy this particular event. Otherwise, the whole thing is 0, and there's nothing to talk about, right? Otherwise, the right-hand side is 0. So if not, then what I have is that I can divide through f of Sn plus 1, Sn plus 1 divided by the Poisson distribution, Pn, Tn. Okay, so now we already know the top part, that is the joint distribution, which is lambda n plus 1 e to the minus lambda Sn plus 1. That is the top situation. The numerator, the bottom is the Poisson random variable, Poisson distribution, which is the following: e to the minus lambda t over n factorial. So after you clear fractions a little, you will get n factorial lambda. Where does the lambda come from? Oh, it comes from here. All right, e to the minus lambda Sn plus 1 minus t divided by t factorial, t to the power n. So this from here to here algebra. Okay, so I just want to mention that this comes from the joint distribution of vector Sn plus 1, and this comes from the Poisson distribution that we proved last time. So I'm not going to belabor the points. Here to here is algebra. Okay, so now we need to do a little bit of adjustment. Okay, because we desire f of Sn given nt, but this is Sn plus 1. So we need to do a slight bit of adjustment only of the indices, right? So now we have f of Sn plus 1 given nt, Sn plus 1 given n is equal to f of Sn given nt, Sn given n. We need to compensate with something. F of Sn plus 1 given Sn nt into Sn plus 1 given Snn. This is nothing but Bayes rule. Okay, how to apply the Bayes rule? We always condition on the same thing. And then you see, if you close your eyes to the conditioning, then this is nothing but Bayes rule. Correct? Yeah. So it's Bayes rule, but you need to be fast with this. Okay, so one of the terms here is easy. All right. So if we look at this guy here, right, what do we notice? Okay, you draw a picture. You have Sn here, you have Sn plus 1, and you have t here. So at point time t here, we have n arrivals only up to this point, because we are conditioning on the event that nt is equal to n. That is this situation here. So we are asking, what is the distribution of the Sn plus 1, given that I know that at this point I have n arrivals. Here in the new for the new arrival epoch, I have one more arrival. So what must have happened here? What must have happened here? You must have one arrival here. So what must have happened here? No arrivals. But we proved a theorem called the memoryless theorem last time, that this guy is exponential. You come in here at a fixed time, the time to the next arrival, we prove that it's exponential. So this guy here is exponential, but it's suitably evaluated. Okay, so now let me complete this. Okay, so we have this situation, and this guy here is exponential. Exponential what? It's lambda e to the minus lambda Sn plus 1 minus t. It's exponential with the length being this. This is the length Sn plus 1 minus t. This is very small, ugly. This length here is nothing but Sn plus 1 minus t. Even worse. Okay. Oh, All right. So basically, we have this, and just now we had, after a bit of calculation, we have shown this. Right. This is the n plus first, and then we will have some cancellation. This is the n plus first, and this is the red part. So what we desire here is the f of Sn given nt, Sn given n. We have to divide this by the red part. And after we divide this by the red part, as with all math, beautiful math cancels. Right? And we are done. This is n factorial over t to the power n in the interval, in the region given by 0 less than s1 less than s2 less than dot 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 less than sn less than t. Okay, I am a little bit imprecise with all the equal signs. I think I should remove all these. Okay. So you see here, what we are using is not much. We are basically just using the properties that we have proved before. Okay, let me go through this one more time before we take a break. All right. So conditional arrival densities. We are interested in this particular distribution. I already know that at time t I have n arrivals, and I'm interested in the distribution of the n arrival epochs. Okay, the n arrival epochs are called S1 to Sn. And the claim here is that you are uniform over this particular interval. And you will think that this looks very not uniform. Then I urge you to look at the one arrival case, in which this can be drawn as follows. Okay? So now we have this, we already know this from a previous lecture, and I'm not going to repeat the proof. I typed out this proof carefully. And so we appeal to Bayes' rule. Now, the only marginally difficult term is this, which we have to interpret. This can either be 0 or 1 only. Okay, it is 0. It is 1 if this is true. That means t is sandwiched between Sn and Sn plus 1. Because there are a total of n arrivals at t, so it must be sandwiched. Otherwise, it is 0. Now, we restrict our attention to this space here. Then we basically do division. This is equal to 1 already, get rid of it. We basically do division. But we know that the bottom is Poisson. And we know that the top is this term here. So there's some cancellation and we get to this point here. Now we need to do some shifting. All right. So we know this guy here because we took the memoryless theorem. And the memoryless theorem tells us that this length here is exponential with the correct length. This length here is Sn plus 1 minus t, which I put it here. And basically now I divide on both sides. And with all beautiful math, you will cancel beautifully and get n factorial over t and beautifully in this particular region. And later on, we'll look at this region in greater detail and talk about order statistics. Okay, so we come back at around 7:45. Okay, 12 minutes break, and then we will resume. Okay, great. So I'll pause the recording. Hello. Hello. Okay. I guess everyone here or one person is missing. Okay, 45. Let's get started. So I just want to remind you, this is the one we can go, right? So I just want to remind you that we proved this result just now. And there are few other things we want to do before we actually look at a particular example. Okay, so these are the arrival epochs. S1, S2 up to Sn. So they are very hard to speak like that. So now we're going to ask a slightly different but related question. It's not too difficult. So how about the joint distribution or joint density of the inter-arrival times? And the inter-arrival times are xn, x1, x2 up to xn. How about the joint density of inter-arrival times? Now, the distribution cannot be the same. The distribution cannot be the same because the domain is certainly different. These are increasing. Okay. Now, these random variables here, xn is not guaranteed to be bigger than xn plus 1 and so on. But the region here of interest is what? Is that all the xi's are bigger than 0, and the sum of the xi's is less than t. That is the region of interest up to n here. That is the region that the density will be non-zero, because this is the allowable region of inter-arrival times. You agree? Just like this is the allowable region of the arrival epochs. Okay, this now here is the region that we allow for the inter-arrival times. Okay, so we have to make sure that we understand the physical situation. So there is a one-to-one transformation between Sn and Xn. All right. So here, remember that S1 is equal to X1 and Xi is equal to Si minus Si minus 1. So here I is in 2 to n. Right. So we can also express this as S1 equals to X1 and Sn is equal to sum up to n of the Xi's. Okay. So what is the meaning of one-to-one? That means that if I know the x's, x1 to xn, then I know the s1 to sn very easily, right? So in particular, all right, we can write the following: s1, s2, all the way up to sn. We can stack this in terms of a vector, and we have another vector here: x1, x2, up to xn. So we can write this as a matrix: 1, 0, all the way. S2 is x1 plus x2. And this is the last row is all ones. You agree? All here are ones. Along the diagonals, we also have ones. And over on the other side is all zeros. Agree? So we can write x and x and s in terms of this matrix equation. All right, so now let's consider a case where n is equal to 2. All right, so s1, s2, we can write this more explicitly as 1, 1, 1 like this. Okay. So what is the determinant of this matrix? 1, right? And after some very painful calculation, you realize that for whatever n, the determinant of this matrix is equal to 1. Okay, I do the n equals to 2 case because I can do this thing very quickly, this determinant very quickly. But for this, you need Python. But you don't Python, you can do this by induction or by looking. All right. But nevertheless, I did for n equals to 2, and the determinant is equal to 1. What does this mean? What does a multivariable calculus tell us? Okay, so in case you forgot multivariable calculus, you realize that the Jacobian, there's something called Jacobian between this and that, between this thing and that thing. So this is a function that takes in a vector and outputs a vector. The Jacobian has determinant 1. And so this is a linear transformation from this side to this side. Right? From this space to this space, we have a linear transformation whose Jacobian is equal to 1. So the value of the density does not change. All right. So if you do not know this, it's okay. I draw a picture for you. Then you will see this, at least for the n equals to 2 case. Hence, the value of the density is unchanged as a result of this linear transformation. So n of xn and t xn given n. And again, I am very lazy. This is my notation for x1 to xn. This is the information theorist notation, and I'm an information theorist. x1 to xn. This is nothing but n factorial over tn. But the region that it is 0 and not 0 changes. The region is that xi is bigger than 0 for all I. This I running from 1 to n. And the sum is equal to 1. It's no. It's smaller than t. This is the region in which the density is non-zero. Okay? So the picture is as follows if you do not know about Jacobians and things like that. Okay? You don't need to know this. Now you need to know this picture, but you don't need to know about what I just said, Jacobians. So S2 and S1. Okay? Where are we non-negative? S1 must be smaller than or so we must be in the situation that S1 is smaller than S2 smaller than T. So S2 smaller than T is controlled by this line here. Right? So where is S1 smaller than S2? Here. Here. Okay? So now this is the region in which we are non-negative or positive. We are positive for the S process. And T equals to 2 of S2 given 2. This is where we are positive, all right? So now for the X process, we are interested in f of x2 given and T equals to 2 of x2 given 2. All right, this is x1, x2. Where are we positive? We are positive here. T, x1, x2 are positive, and x1, x2 must sum up to less than t. This is the region. Because this is the line for which x1 plus x2 is equal to t. So what this matrix does here, right? What this matrix here does is that it transforms us. It does a linear transformation of this region to this region and otherwise. This matrix is invertible because the determinant is not 0, and in fact, the determinant is 1. And when your determinant is equal to 1, your volume is preserved. Hopefully, you remember this also. Year 1 things. The volume is preserved. Look at this. From my beautiful picture, the area of the triangle is preserved. Right? So basically, we have easily derived the value of the density for the X process, which is the inter-arrival times. For inter-arrival times. Rather painlessly. Any questions about this? Any questions about this? So I cannot draw 3 dimensions, it will be too painful. Right? I attempted to do some 3-dimensional thing last time, which didn't turn out so well. So what we have done up to this point is, okay, we have found after the break, we have recalled that the density of the S process, basically the arrival epoch, is given by the following. All right. Now we want the density for the X process. Okay, the X process is a sequence of inter-arrival times. One very important thing is that when we do this sort of things, you must be sensitive. Clearly, condition on Sn, right? Condition on Nt equals to n. Condition on what we condition on Nt equals to n. S1 does not have the same distribution as S2. Now, suppose I go into the living room and the TV is on and I saw that 10 goals were being scored. Certainly, the second goal is scored after the first goal, right? But what about the sequence of inter-arrival times? When I condition on the fact that NT is equal to N, I saw 10 goals. Actually, the distribution of x1 is the same as the distribution of x2 and so on and so forth. Symmetric. All right? And this can be seen here. This can be seen here. This distribution is symmetric in the axis. Because when I replace x1 by x2, nothing changes. All right? When I replace x1 by x2, nothing changes. This is remark. F of xn given nt, xn given n is symmetric in the x1 up to xn, clearly. So the distribution between two goals, when you walk into the room and you see that there are already 10 goals being scored, the distribution between the third goal and the fourth goal and the seventh goal and the eighth goal is the same. It's symmetric. You can replace 2 by 1 and 1 by 2. You agree? Yeah, good. Super. Any questions? Okay. The people at home have no questions. The people here have no questions. So it must be crystal clear. Okay, so let us connect, and this is very important. The last theory bit I want to talk about is very important because I tell you, I will ask you something about this in the next quiz. Okay, the people at home, please take down this also. I will ask you something about this. The people here, take this down, remember this. There is the connection to order statistics. Okay, so you know what order statistics? This is something in statistics. I have a sequence of, say I draw a sequence of IID random variables, U1 up to UN. And these U's, I just want to introduce you to order statistics. They are random variables, they are independent and identically distributed, and have some distribution on 0t, the closed interval or open interval, whatever. All right, we can create new random variables U1, U2, UN, like this. What is the meaning of this? I order them so that U1 is less than U2 is less than ... UN. What happens if they are the same? Okay, they won't be the same. Continuous random variables. With almost surely they will be the same. So don't ask me this question. So the U's are the U sub. These are order statistics relative to this. So in statistics, people devote their whole lives to studying order statistics like this. Okay, and now we will devote 20 minutes to studying this. Okay, so we will study the appearance of order statistics in the context of Poisson processes, in the context of conditional arrivals. So if you want to study order statistics, this is what you will be studying. You draw a sequence of ID random variables, and then you want to order them, and you want to study, for example, the distribution of the K1. All right, that is interesting to some people. Okay, or you want to study the distribution of largest one. That's relatively easy. Okay. So this is order statistics, and we want to somehow study them in the context of what we have already studied. Okay, so now let UN, as I mentioned, be just a sequence of random variables that are IIT in 0t and uniform. Okay, so let me be precise here, and it is open and right hand side is closed. So what is the meaning of this? To be precise, for any UN in 0t and we have that f of UN is equal to 1 over t power n, which is 1 over t to the power n, whenever 0 is less than ui is less than equal to t for 1 less than I less than n. Okay, so the picture is as follows. We have that no matter what I you choose, this is f of ui, u is better. When this is t, then the distribution, this is t. This is u, this is 0, this is 1 over t. So we have a bunch of random variables, I, indexed by I, running from 1 to n, and they're all uniform in the interval. They all have this distribution and they are independent. Okay? There's no collection of random variables that can be simpler than this. But we'll see that this beautiful collection of random variables actually appears in Poisson processes. So now we have studied Poisson process. You see that not only do we have exponential random variables, Erlang random variables, Poisson, of course. Just now I talked about geometric, negative binomial. You will come across in the homework this week. We will also have beautiful IID uniform random variables. So from a simple construction, we can derive almost every random variable you can think of. Cool, right? All right. In case you don't think this is cool, we will prove something that's cool. Right. So, what's the fact that we want to show? Okay. So, fact. Both f of Sn given nt dot given n. So that's the distribution of Sn conditioned on the fact that nt equals n, and f of un dot as well as f of xn given nt dot given n. So that's the distribution of xn conditioned on the fact that we have already seen n arrivals at time t are uniform over the space in which they are positive. Now, actually, we have already seen this fact for this distribution and this distribution. We have already understood this fact. Hopefully, by now you understand. They are uniform over the space in which they are positive, because these two objects here are both, too big. These two objects are both all equal to n factorial over t power n. They don't depend on the argument as long as the argument satisfies some condition for which the density is positive. We have already seen that. So this statement, this fact here only applies to what we have not colored in red, which is this thing here. But it's also obvious that this is uniform. This is also uniform, right? On the region that it is positive. Look at this, it is only positive in this particular region. Okay, but the letter f of un equals to 1 over tn for ui in 0t for I. Okay, is n factorial smaller than f of Sn given nt dot given n. Of course, I've already said this. Look at these two. This is n factorial bigger than this. So I'm just being tautological here. I'm just being very repeating myself because we had already proved this, and now we are writing this down based on the distribution of the UIs. Okay, so I've already said this. So let us see this more explicitly, but this is already something I have alluded to previously. To see this more explicitly, let Sn be equal to S1 up to Sn be defined. Now, in the past we defined this to be the arrival epochs of a particular Poisson process. But now, let us not define it as the arrival epochs of the Poisson process, but as the order statistics. And I will make this precise of the IIDU process, UI process. Okay, so what I mean is the following: S1 is equal to minimum, just to be precise, U1 up to UN. Okay, so that's the smallest guy. S2 is the minimum U1. How to say this? How to say this properly? U1 up to UN diff S1. Okay, so we have the minimum. So this you can think of it as the minimum. The S1 is the minimum. S2 is the minimum of the rest, not S1. Okay, and similarly, SK is the minimum of U1 up to UN. Take away S1 up to SK minus 1. Okay, so this is just a definition. So now they are not the they are basically not the arrival epochs, but you can think of them as the order statistics of the UI process. So what's happening here is the following. So you have this situation where the U1, U2 are non-zero, is non-zero over this particular square. It's a square. Okay, this is where it is non-zero. And the value is how much? It's of course 1 over t squared. Agree? So that's the height above the iPad. Okay, now let us consider S1, S2. S1, S2 up to t. Now, where do the order statistics take their value? Where do the order statistics S1, S2 take their value? S1 is the min, S2 is the max in this particular case, but I only have 2 guys. All right, we only have 2 random variables. So they take their value here. But this region here is exactly the same as that of the arrival epochs, conditional on the fact that nt is equal to n. We have drawn this picture just now. And what is the value here? What is the height here above the iPad? Well, it is nothing but 2 over t squared. The height. Why is the height this? Because the whole volume must integrate to 1, right? And what is the area of this light green rectangle? The area is equal to t squared over 2. So we need this to be 2 over t squared for us to integrate to 1. All right. Here on the right hand side is easy. You just compute the area here is t squared. So you need to normalize by this guy here. So the order statistics take on values uniform in this particular region here. But this is exactly the same as the arrival epochs of a Poisson process when I condition on nt equals to n. I drew the same picture just now. So this is equal to f of t, f of u2. And this is equal to f of s2 given nt, s2 given n. We need this to be 2. Okay? So now let me make a few more comments. Note that in general, the n cube, so it's a cube of length t in n dimensions. So this n cube, right, it is basically a generalization of this to n dimensions. You must think of an n cube, all right? Note that the n cube can be partitioned into n factorial regions, right? So we can index each of these regions by a certain permutation. For every permutation pi, a permutation is basically a bijective map from these integers to these integers here. Okay. For every permutation, there is a region associated with it. Basically 0 less than u pi 1, less than u pi 2, less than dot dot dot, less than u pi n. So this region here in particular, look at this. This is the region in which pi is the identity permutation. Okay, pi is the identity permutation in the sense that I'm not permuting anything at all. Then this is the anti-identity permutation. So pi 1 is equal to 1, pi 2 is equal to 2. Here, pi 1 is equal to 2, pi 2 is equal to 1. We are flipping. So we are only interested in the identity permutation for the arrival epoch process condition on nt equals to n. Understand? Okay, so let us do something even more complicated. Okay, so later I'll do the n equals to 3 case. By symmetry, each region, each sub-region indexed by pi has the same volume. Okay, so look at this picture here. This is the simple case. This has volume or area t squared over 2. And this other permutation has volume t squared over 2 as well. Okay. Hence, the density, the conditional density, this is another way of looking at the conditional density. F of Sn given nt, Sn given n must be n factorial times of the U process. Okay. So that's another interpretation of conditional arrival densities. That all the S's, okay. So when we condition on nt equals to n, this event here, the Sn process, the sequence of arrival epochs, is distributed the same way as the arrival epochs, as the order statistics of the order statistics of ui, where ui is uniform on 0t inclusive iid. All right. So we have seen this here. All right. So in the case where n is equal to 3, what are our permutations? All right. You can have u. This is the identity permutation. I think it's better to write, yeah, u1, u2, u3. Of course, u1 less than u3 less than u2. This is, and then u2 less than u1 less than u3, u2 less than u3 less than u1, and u3 less than u2 less than u1, u3 less than u1 less than u2. So you have the size of the permutation. Okay, I'm making up notation as I come. It's 3 factorial, right? I think it's not like this. The number of permutations, let me just do this for n equals to 3. It's 3 factorial. In general, it will be n factorial. And that's where the n factorial comes from. That's where the n factorial comes from when we talk about the distribution, this distribution here. Okay? This is basically n factorial over the uniform distribution of the IID process, f of un. So this is n factorial larger than this. And that's because we only care about one slice of the region, this slice. And previously, I drew a 3-dimensional picture for the n equals to 3 case. Okay? So for the n equals to 3 case, we only care about the identity permutation, which is this guy here. And this is 1/6 of the total space, of the total volume. The total volume is T cubed. All right, this is 1/6 of it. Any questions? This part is very deep. It's not very deep, but it's actually very interesting. Okay. Any questions? So this is yet another explanation. Another explanation for the conditional arrival distribution f of Sn and T, Sn given n. is n factorial over t, and in the region where the density is positive. Okay? So today we focus on this formula. Any questions on this? Okay, if not, let us do one last calculation before we do an example. Okay, so I promise you this, right? If you walk into the living room, this is the third time I'm saying this. If I walk into the living room and I saw that 10 goals were scored at time 70 minutes, what is the expected value of the time that we scored the first goal? It's 70 divided by 11. Let's prove this. Okay, and you can prove this by all the theory above. Okay, so what's the density of S1 given, actually the book does SI, okay, but I'm just going to do S1. Okay, NT equals to N. Okay, what's the distribution of the first arrival epoch given that at time t we have already seen that? All right. So let us remember that this is the minimum, has the same distribution as the minimum of U1 up to UN. Okay, as I wrote above. So let's consider the complementary cumulative distribution function. Okay, let's consider this. Why do we consider this? Because I promised you that I want to compute expected value of S1 given NT equals to N. To compute the first goal, the expectation value of the first arrival, given that I have n arrivals in an interval of time t. I want to get to this point. So I calculate this guy here. Why is it useful to calculate the first guy to get to the second expectation? To get to the expectation. Why is it useful to calculate this to get to this? Do you remember that for a non-negative random variable, expected value of z is equal to a probability of z bigger than z dz, 0 infinity. So we prove this. This is called a layer cake representation. So if I manage to get a handle, on this guy, then it will be relatively easy to compute this by integration. Right? So that's our strategy. And this should be our overarching strategy as well. Okay, so because this first term here is very easy to calculate, I claim. This first term here is very easy. So let us compute this. This is nothing but probability that the minimum of U1 up to UN is bigger than tau. Right? This is the definition of the S1 to Sn given NT is to N. Right? The S1 is the minimum. So basically, I just plug in the benchmark. Right? Now, if the minimum of a bunch of random variables is bigger than tau, then surely everybody is bigger than tau. So this is equal to the probability of intersection of UI bigger than tau. You agree? It's just logic, right? But everybody here is very beautiful and nice and independent, so we can just do this. Everybody is independent. So now, UIs are what? I drew a picture here, right? The UIs are this random. This has this distribution here, right? They are. Oh, I shouldn't cut this. The UIs are uniform. They are uniform here. So what am I doing here? Basically, I am looking at what the chance that is bigger than tau here, and the chance is here. All right. So this reduces to product I running from 1 to n of t minus tau over t. And this can be simplified. Right? Okay, so basically, what do we use here? We use that the distribution of S1, the distribution of S1, this distribution is the same as the conditional, as the order statistics, as a mean of U1 up to UN, the first order statistic, where the UIs are IID and uniform on 0T. So we love IID random variables because they have this beautiful properties, like you can just decouple them into product, right? Beautiful. That's why I don't like the SNs. Furthermore, these are like, in general, they'll be Erlang. Condition on this headache. That's why we need to resort to order statistics. Then this becomes beautiful because this is minimum bigger than tau, means that everybody is bigger than tau. But everybody is independent. They are all independent, so we have this situation here. And we can evaluate each one of these guys with this, this. So now I give you the promised result that expectation value of S1 given nt is equal to n is something that you intuitively would expect. And I will show you that you intuitively would expect this if you draw a picture. Okay? So this is nothing but the integral of the complementary cumulative. We need to carry the conditioning around the tau 0 to t. Agree? This is what we proved. Layer cake representation. So now we have t minus tau over t, I guess here. Power n, the tau integrate from 0 to t. So now we have to worry whether we know how to integrate this kind of things. But this is a polynomial. This is a polynomial, so hopefully we can integrate this. So we have t minus tau raised to the n plus 1 over minus 1. T0. So 1 gets killed, and we have this one. T gets killed, and we put this in as so. T. Oh, something's wrong. Oh, no. When we integrate this, we have this n plus 1 with a minus here. Otherwise, it doesn't work out. This is t over n plus 1. Okay, so this is my promised result. So what is the situation? We have a total time tu. This is when you walk into the living room to watch the football game. And then, okay, 10 goals, maybe 2 difficult for me to draw. You will see that there are already 3 goals. The score is 3-0. Okay. So the second goal is likely to be here. The first goal is here, and the third goal is here. There will be 4 spacings. 3 goals means 4 spacings. 1 spacing, 2, 3, 4. Okay. And the expected value of the time of the first goal as 1. And t equals to 3 is exactly t over 4. That's what we proved. So this is some result that you should remember for the rest of your life. Okay, so this is what I promised you. All right. Okay, so now we can actually, any questions here? Any questions from the people at home? Any questions? Any questions? No? Very clear? Yang Jie. I only know one name. Because you are in my lab. Clear? Okay, so now if the first goal here, the first arrival is at t over 4, when is the expected value of the second arrival? Let's do that. So look at this. We can easily get the, okay, what do you think is the second arrival? Okay, I think it's t over 2. And this is 3t over 4. Let's prove this. Who says that it is this, right? Let's prove that the expected value of S2 is what we think it is. How do we do this painlessly? That means no pain. So we know that this is true. So expected value of S1 given NT is equal to N is equal to T over N plus 1. We prove this. But S1 is exactly X1. Right? So we can do the following. Same thing. So now I'm interested in SK, where SK is XI, I already the kth arrival epoch. Okay, that's the kth goal. So I'm interested in SK. SK conditional on NT equals to N. So as I mentioned, this is nothing but sum up to time K of Xi conditional on NT equals to N. Right? But expectation is linear. So this becomes K of expected value of Xi given NT is equal to N. Now, what is expected value of X1 given NT equals to N? Well, that's T N plus 1 here. So we know the first term here, if X is I is equal to 1, we know this. What about X2? So in general, Xi given NT equals to N is equal to T over N plus 1. Because the Xi's given or not given, NT equals to N are symmetric. I already told you, symmetric and identically distributed. Identically distributed. They're the same distribution. So certainly they have the same mean. And we know the mean of the first one. So the mean of everybody else must be the same. So this becomes IK over N plus 1. So it means that, all right, let me go through this a little bit slowly, okay? So we have proved that expected value of X1, given that we have N arrivals in time in the interval 0 t, this is T over N plus 1, and it's illustrated in this picture here. This point here is T over 4. Okay? S1 is the same as X1, so this is equal. Okay, so this takes on the same expectation. Now, condition on the fact that NT is equal to N. All the x's have the same distribution. They are symmetric. Why? Because when we derive the density of x here, when we derive the density of x, right here, let me cut this out here. You see that this is completely symmetric in the x. You see that this is completely symmetric. If I replace x1 with x2 and x2 with x1, nothing changes. There's symmetry among the x's. There's no symmetry in the s because s2 must be bigger than s1. All right? That's because, right? It's because the addition here is commutative. Right? X1 plus x2 is the same as x2 plus x1, commutative. Right? And this does not depend on x. So the x's have the same distribution. So clearly they have the same mean. This has the same mean as x1. So all these people inside here have the same mean. And all of them have the mean this is not this, this is kt over n plus 1. All of them have the mean t over n plus 1. So k of these people have the mean kt over n plus 1. Do you agree? So in particular, for example, in this picture here, if k is equal to 3, then we have that we have proved that the expected value of S3 given NT is equal to 4. 3 is equal to 3t over 4. Okay? Agree? Any questions? I went through this 2 times. So at this point in time, we have completed. Any questions? Zoom people, any questions? I still have half an hour to do my question. Let me see whether I know anyone here. Not too many people. Luo Zijian, any questions? He asked me questions. No, sleeping. Okay. Any questions from the audience here? All right, so now I want to do question. I come to the end of the discussion of Poisson processes. Okay, so that's all the material. So I wanted to do an example question for you to show you that actually this is quite interesting. Okay, so we have already done something like this just now. This is exercise. Let me use the blue pen now. 2.18 of Gallager's book. I could have set this as a homework question, but I didn't. I do it for you, like a tutorial. Very nice, right? And this question here is a good question. It illustrates a point. Okay, so let's see. A. So now consider a Poisson process. Whenever you talk about Poisson process, we need to specify the rate with random rate lambda. So usually our rates are little lambda, like this lambda. This might, I use this to denote, I use this to denote capital lambda. Right? So now my rate is random. The Poisson process is random rate. Oh, very exciting. Okay. And what we need to define the distribution of this random variable. So this random variable is f lambda lambda is alpha e to the minus alpha lambda, and lambda bigger than 0, 0 else. So our rate, first and foremost, right? The rate must be non-negative random variable. Because the rate of a Poisson process must be non-negative. So you cannot have Gaussian rate. Very funny, right? Gaussian rate. You could have negative. The rate cannot be a negative random variable. So it must be non-negative. And so this is a good distribution. Okay. So consider a Poisson process random rate. Okay, so the first question is, what is probability of nt equals to n condition lambda is equal to lambda? Okay, so once I know, okay, this Poisson process has a name nt, say. So once I know that my rate is little lambda, then it's nothing but Poisson, right? So everyone should get these marks, okay? So this is lambda t to the power n e to the minus lambda t over n factorial, n running from 1 to. So it is a matter of understanding the question giveaway. Any questions? Any questions from the Zoom people? This is the warm-up. Warm-up. Now we go into the exercise. Okay, what's the exercise? This is where it gets interesting. Probability of nt equals to n. So what would you do? I already said this just now, maybe 2 hours ago. What would we do? Yang Jie. Oh no, maybe I can call someone, I'm sorry. Okay, Zoom people, what do we do? Yes, law of total probability, yes. So we will integrate this. Integrate probability nt equals to n condition lambda equals to lambda f of lambda lambda d lambda. Okay, and then we integrate this from 0 to infinity. Okay, so we do this carefully. So we have the Poisson here, e to the minus lambda t over n factorial, and this guy here is given by alpha e to the minus alpha lambda d lambda. Okay, so when you encounter this sort of things, you either cry or you think. I prefer to think. What can we do? This is Erlang something. we can see this. What can we see that is aligned? We need to massage this. You need to massage this so that this becomes aligned. How can you see that? Okay, see, this is the exponential part. And lambda is the polynomial part. Lambda power n is the polynomial part. So this is aligned. Can you see? So we need to massage this so that we get aligned. So we have a distribution. We know that every PDF has to integrate to 1. So we need to massage this into an align. Okay, massage. So we have this, everything that has not to do with the integration outside. So we have alpha t to the power n and everything inside. Okay, so the n factorial I want to keep inside because align has n factorial. Okay, so other things that I want to keep inside include lambda to the power n e to the minus alpha plus t lambda d lambda. So we have this. This is almost almost. Okay, so let's move this a little bit to here. This is deliberately written this way. So I compensate this until it's aligned. T power this lambda power n over alpha plus t power n. I can certainly do this. This is some integration trick. So now, oh, this is really aligned. We can put this as z to the power n e to the minus z over n factorial dz. Correct? Oh, we need to compensate this plus 1 here. Okay, this is too fast. So let's do it slowly. Okay. So now we do change of variable. Okay, we let z with this. Then dz is equal to d lambda alpha plus t, right? So you need to replace this d lambda by dz divided by alpha plus t. So we this plus 1 here. Change of variable. You need to be skillful in integration. When I was young, I was very skillful in integration. Now, not so good, but I can still do this. Okay, so the claim here is that this is Erlang of order n plus 1 with rate 1. This is an Erlang distribution of order n plus 1 with rate 1. Why? Erlang distribution of order n with rate lambda is what? It's a lambda to the, okay, so it's f of, this is Sn, right? F of Sn t is equal to lambda to the, this is n minus 1 factorial, I remember, e to the minus lambda t, I remember. This is lambda n t to the n minus 1. This is t bigger than or equal to 0. Yes, correct. I remember this correctly. Why? So the thing that I cannot remember is this n and this n. The rest I remember. But Erlang is a generalization of exponential. And I know that Erlang of order 1 is exponential. So if I put in 1 here, then this gets killed. This gets killed also 0 factorial, right? So if you get rid of the red part, oh, you see that the remaining part is exponential distribution. So I'm right. That's the way I check that. So now, if rate is equal to 1, then we degenerate this into, oh, we got rid of this. Then this is 1, and this is t to the power n plus 1 e to the minus t over n plus 1 factorial. So we raise this by n plus 1, we get exactly this distribution here. Cool, right? This is a very painful way of doing it, and I'll show you a nice way. So the point is that this integral here is equal to 1. So we are left with, what are we left with? Alpha t to the power n. We can write this in the following way. Alpha over alpha plus t over alpha plus t raised to the n equals to 0, 1, 2, and so on. You can write it this way. And this way makes you think of something. It makes you think of something, right? Think of something that starts with the letter G, geometric, right? So I did something similar before. And so you'll notice that how important what I'm telling you is. If I tell you something more than once, it's very important. So this is an integration way, and you need some integration gymnastics like what I did, right? So we don't like to do calculus gymnastics. We like to do thinking. This is doing, or this is manipulation. We don't like to do gymnastics. So can we do something that is better? All right. So the above is too cumbersome, even though it can be done. Let's do a proof 2 of the same result. Okay, so this actually is important. This is just for side information. So this actually goes down to here equality. Okay, the above is too cumbersome. Let us use a smarter method. Okay, so we observe that the solution from the cumbersome method can be written as PQ. Oh, let's not introduce new notation. P1 minus Pn, where P is equal to alpha over alpha plus T. Right? So this reminds us of something. N starts from 0. Okay. Okay. Note now that probability NT equals to N. All right, look at this quantity. For a Poisson process of rate lambda, let me say fixed and deterministic. Deterministic means not random. Rate lambda is a function of only lambda t together. All right. So now let me make this a little bit more pedantic. N lambda t. So n lambda is a lambda rate Poisson process. A lambda rate Poisson process taking on the value n is only a function of lambda t, the product. Okay. Why? Because this is nothing but e to the minus. You see that the lambda and t always kiss each other. They always stick together. Okay. So the point here is that lambda t for this basically random variable, this random variable I've written down, is the same in distribution as n lambda t 1. Oh, why? I've already written down this n lambda t equals to n. It is nothing but this guy here. Right? But as you can see, probability of n1 t equals to n, what I mean is that lambda t equals to n is the same thing. Right? It's exactly the same thing. I'm evaluating the rate 1 process at time lambda t. Okay? Now, another fact of the matter here is that lambda, the random variable lambda, was exponential alpha. Right? And the claim here is that lambda times t, where t is a deterministic quantity, is exponential alpha over t. This can be shown by transformation of random variables. Okay, so we have a certain random variable that's an exponential. We take that random variable, we multiply by a fixed number. It is alpha over t. How to check this? You know, the expectation of lambda is 1 over alpha for exponential random variables. That's the way to check. So the expectation value of t lambda is t over alpha, which means that this guy here, if it is exponential, it has the inverse of this as its rate. Okay, so I'm going to get rid of this. Okay, this is a bit fast, but you should be able to prove this. Okay, so what is the meaning of n lambda t? Okay, so that was what we would like to evaluate. All right, because if we can do this, then we would be able to tell. Okay, so if we are able to control or get a better understanding of n of lambda t when this is random, with distribution given by exponential alpha. So this entire thing here is exponential alpha over t. Okay, this is exponential alpha over t. All right. If we are able to get a handle on this object here, then we will be able to understand the Poisson process with random rate lambda. Okay, let me just write it down before I explain more. So what is the meaning of this? This represents the number of arrivals of a Poisson process of rate 1 before the first arrival of an independent Poisson process with rate alpha over t. Right? We did this just now. That's why I did the example for you just now, where the inside here is what I call t. Now I just change it to lambda t, where the lambda is the random variable. Lambda t has exponential distribution. Okay, so we have already done this. So the probability distribution of n lambda t equals to n, all right, is basically geometric. And geometric with the following picture. Okay, so we start from 0, and we are interested in the number of arrivals of the Poisson process of rate 1. This is the Poisson process of rate alpha over t. We are interested in the number of arrivals of Poisson process of rate 1 before the Poisson process of rate alpha over t. That's the picture you have in your head. Right, that picture with the green and the red. How many green things before the red thing? It could be 0. Right? The way I've drawn it, there are 4. Okay, so the combined process has rate 1 plus alpha over t. Right? So now what we have here is, this is nothing but, what is the success? The success is alpha over t over 1 plus alpha over t raised to the power 1. And the number of failures we have is 1 over 1 plus alpha over t raised to the n, where n can be from 0, 1, and so on and so forth. So this becomes t over alpha plus t raised to the n, and alpha over alpha plus t raised to the power 1. N can be 0. So basically, we can think of this as merging stripping. And we need to figure out the rate of the respective processes. So based on the Poisson process of rate lambda, I basically rescaled it so that it is now a Poisson process with rate 1, this. But now so this is a rate 1 Poisson process, evaluated at lambda t. Now our lambda t here is actually a random variable in the context of our question. And it is this particular random variable which we have figured out. The rate is alpha over t. Okay, and so this quantity now represents the number of arrivals for the Poisson process of rate 1, these green things here, All right, and this is now a Poisson process of rate alpha over t, because it represents the first arrival of a Poisson process with that rate, or the first inter-arrival time, which is exponential. So now we have already thought about this, and so now we need to have n failures before the first success. Okay, which is exactly this. After you clear fractions a little. Okay, so this is a geometric distribution that starts at 0. Okay. So now I would like to do one more part, and we'll call it a day. We will not do part D because it's the same thing. Yeah, I mean it's not the same, but it uses the same tools. So now let us try to find the conditional arrival. What is the distribution of the rate given that I see nt equals to n? All right. So I see that, so this is a Poisson process with random rate. I see that at time t, we have n arrivals. So what is the distribution of the rate? Okay, now the rate is random. So the only way we can do this, at least the only way that I know, is to use Bayes' rule. Now f of lambda over probability nt equals to n. Okay, so we have every information, we have all the information. This guy here is nothing but Poisson, e to the minus lambda t over n factorial. Now this guy here is exponentially distributed, alpha e to the minus alpha t. And the bottom here is geometrically distributed, it's alpha t to the power n over alpha p n plus 1. Okay, so as with beautiful math, things usually cancel. If things don't cancel and you get something very ugly, math is never ugly. So you are wrong. All right. So in this case, I think I am right. And so we have lambda n e to the minus lambda alpha plus t raised to the n plus 1 over n factorial. N starts from lambda starts from 0. So this guy has a name. So this is Erlang order n plus 1 rate alpha plus t. So once we identify with this distribution, Erlang distribution, we are safe. Because I'm very afraid that people here would do a bunch of manipulations, complicated manipulations, and in the end up with what? With a distribution that does not add up to 1. Then you are wrong. No matter what you do, when I ask you to derive a distribution, what do you check? You check that it adds up to 1. Now I already checked that this adds up to 1 in my head, because this is Erlang of order n plus 1 with a certain rate. So it is correct, or at least it's not wrong. Cool. So this question here, especially part B, is very useful for understanding of splitting and join and merging. Okay. So with that, actually we complete our discussion of Poisson processes, and next time we will talk about Markov chains. All right. So you have this homework assignment, and I actually designed a couple of questions inside that. I don't just copy from Gallager's book. And this homework assignment, I actually am very proud of it because I designed one from that. The problem 4 is a quiz problem from previous years. Okay, but problem 5, actually in a class on stochastic processes, right? Some instructors expose students to martingales. That's another family of stochastic processes. But we won't have time to talk about martingales. So I let you learn about martingales in the homework question 5. You can do it. I'm very confident. And question 6 is actually optional, but you can play around with it. Okay? So I thank you very, very much for showing up today, which is recess week. Any questions, just let me know. And we will resume office hours as usual next week. Okay? And we have 7 more lectures, I guess. We can do a lot of good stuff. Okay, thank you very much. What is time reversibility? You mean time reversibility in the context of Markov chains, right? Yeah, we probably will talk about that later on. Yeah, we'll talk about reversibility of Markov chains later on. Okay. Or in the context of Poisson process, what page? I don't really know. But you can talk to me offline. Okay. Cool. All right, guys. Take care and have a good night. Let me stop the recording. Thank you.